Hello, everybody, and welcome to another episode of Dome to Home.
Hey, everybody. Welcome back. Yeah, if you're new here, my name's Rémy. I'm an astronomy student at CU Boulder and a presenter at Fiske Planetarium. And I'm running my hand into things below me. We have...
Hey, everybody. My name is Jeremy. I'm sure some of you know me by now, but I also work at Fiske Planetarium, obviously. I work as a navigator, an outreach presenter, and kind of just an overall assistant of educational programs. So everything you are seeing over here on the dome for us today is going to be controlled live by me. And then Rémy is going to be talking us through all this cool science of landing on Mars.
Absolutely. And also helping us is Tara over in the chat. She's going to be our chat moderator and question master for the day. So if you have any questions or comments, feel free to drop them in the chat and Tara will either answer them or send them our way, either down here or over here, wherever it happens to be. So we'll have time to answer your questions live at the end of the show as well. So if there's something like big, you can go ahead and hold on to it and ask it at the end, or just ask it through. We'll be sure to answer everyone's. So anything you're curious about, you've got 3 experts ready to help out. So don't hesitate to ask, all right? So you may have guessed by the title, and Jeremy said we're going to be talking about how Perseverance is going to land on Mars. We talked about planning, we talked about launch and going to space, we talked about what it's going to do when it's there, but how does it go from being a hurtling spacecraft traveling at, tens of thousands of miles an hour to a rover casually cruising the surface of Mars at 1/10 a mile per hour? And that is the tricky part. So landing is notoriously difficult. To get off Earth is a challenge, of course, but it mostly consists of going fast enough. Landing, however, requires you to just undo all of that and slow down. So to get off the Earth, you have to be traveling at 25,000 miles an hour. But if you hit the ground at 25,000 miles an hour, that's a no-go. That's an absolute no-go. Did you know that of all the missions to Mars, of all the space agencies in the world, only 40% have been successful? And a lot of those failures occurred early on in the process, as people were still figuring out spacecrafts and spaceflight, but that's still not a huge percentage. That's like an F. Humans have an F in Mars travel. So if you feel bad about your grades, just remember, we've got an F going to Mars. It's okay. So, there are some early attempts that never even made it off the Earth, and some failed along the way, some missed their target, but every failure is a chance to learn, and we've learned a lot. So, the first spacecraft to successfully fly by Mars, so not even orbit it, was Mariner 4. And that was launched by NASA in late 1964. And I think, yes. So that's what Mariner 4 looked like, your classic satellite here. So 1964, we first just fly right by Mars. We take some pictures and are like, hey, Mars, by Mars. So the first successful orbiter, so that's something that actually orbits Mars, goes around Mars, was launched by the Soviet Union. It's called Mars 2. And that wasn't until 1971. So it took, 7 years?
Mm-hmm.
Yeah, 7 years. I know math, to actually orbit Mars. And its lander failed, but Mars 3 landed successfully. And it stayed in contact for about 15 seconds. And it had this little rover. And I love this rover right here. Whether or not it actually deployed, it's not clear because the lander lost contact. I really hope it did, though, because I just love the idea of that hopping around Mars. The first lander to actually successfully operate, though, is the Viking 1 lander in 1975. So it's more than 10 years after the first flyby. And since then, only 8 spacecraft have successfully landed on Mars out of 14 attempts. So yes, that is a model of Viking 1. That's not Mars that it's on right there. That's like a cutout background and some sand for a nice photo shoot. But that's what it looks like. So 8 out of 14 attempts. And the question is, why? Why is that so difficult? So, aside from the complications of launch and actually getting to the right place, the primary challenge for landing is, maybe surprisingly, slowing down. So here on Earth, we've got a nifty atmosphere to help us with that. So as a spacecraft enters the atmosphere, it's exposed to drag, friction, things like that, starts slowing it down because there's all this stuff, the air in the way. And that slows the spacecraft down considerably. but it also heats it up. So you might recognize some of those. Yes, awesome. Those pictures where it's all heating up. So they've got heat shields in the front, right? So that your spacecraft doesn't burn up. So that slows it down. You also have to make sure you're coming in at the right angle, because you might bounce off like a rock skipping over water. If you're too steep, you just get too much pressure, too much heat, no go. So trajectory is really important. But the thing about Mars is that it doesn't have as much of an atmosphere. Its atmosphere is extremely thin, and we've talked about that. It's about 1% of Earth's, which means it doesn't have nearly as much of a slowing effect on a spacecraft. So, we can try to use Mars's atmosphere that way as much as we can, but even at just the right angle, any spacecraft is just going to go crashing right into the ground, which wouldn't be very helpful for anyone. It also heats up the spacecraft quite a lot, which would endanger scientific equipment. So what else can we try? Some of you have probably already been thinking about it, but maybe parachutes. So parachutes are fantastic for slowing down here on Earth. Ask any skydiver. So, sure, you're going fast now, but once you deploy the parachute, it'll catch the air in the fabric, slowing you down. We even use this in the Apollo missions, right? To slow down more after using the little atmosphere trick, right? There we go. There's the Apollo missions. So do you notice the problem here, though, when it comes to Mars? Yeah, the lack of air, right? Parachutes depend on air. So remember how Mars' atmosphere is 1% as dense as Earth? So to catch the same amount of air on Mars, you end up needing a parachute 10 times as large as you would need on Earth. And, oh, awesome. I happen to hit a question here. How would a parachute work with Mars gravity? So there is less gravity on Mars, which means you wouldn't end up falling as fast. But because there's no air, that's the biggest difference with a parachute on Mars. It just isn't going to work as well. So there's also the problem that parachutes can only get so big before they start being more of a problem than a solution. So you can't really have a parachute hundreds of feet across like you would need on Mars. So a parachute just isn't going to cut it. So new solutions are needed. So let's think a little bit. Have you ever done one of those challenges where you have to build a little contraption to keep an egg safe when you drop it from a building? So what if we did that? What if we just didn't slow the egg or spacecraft down and we just built it to withstand the impact? And we just had it land on some soft stuff here. That's, I believe, an Apollo capsule again. You've got the floaties there and it hit the water. That's nice and soft. Maybe we landed on some nice pillows we throw down. We've got some pelicans landing on water, as they do. So what if we just build it to withstand an impact? And I'm just gonna tell you right now, it's just going too fast. There's too much force involved, and there's some very, very sensitive scientific instruments on board. So we can't just drop it from orbit with a few pillows and call it good. So we really, really do need to slow the spacecraft down. So, what can we do that could slow the spacecraft down that doesn't actually depend on air in the atmosphere? What about we've got, Varric is in the chat here. What if they put little boosters on the bottom like the Apollo missions? Awesome. Retro rockets. Little
ding,
small
ding, ding.
rockets.
We have a
yeah,
winner.
You got it. Varric's on top of it. So we've got retro rockets. They're just little small rockets, right? And they point in the opposite direction of motion. So you can slow down or turn. So in the case of a lander, the rockets would point up. So there can be a force pushing up against the downward motion of the lander. So you can see there, you've got something coming down like that. If you've got something pushing you up, you'll slow down. But even that can't overcome the speeds of a lander dropping onto another planet. So we're kind of at a loss with each of these methods alone, right? And on top of that, whatever we choose has to be automatic. We aren't there to control it. Mars is so far away that there's a communication delay. So sending a signal might feel instantaneous here, but to send a command to Mars, it could take up to 20 minutes. So that's 20 minutes where the spacecraft is trying to tell us something, and then 20 minutes for us to respond. And it's 40 minutes to tell the spacecraft to avoid an obstacle. And by the time the first signal even got to us, the lander crashed, which, as you can imagine, isn't all that great for the lander. So whatever method we pick, we have to make sure that the lander can do it all on its own. And honestly, no single method works for landing a spacecraft anywhere, especially a place like Mars. Every lander sent to Mars, and things also coming back to Earth, have used a combination of the methods we outlined, though in different ways. So let's take a look at our first successes here. Or let's take a look at the ways that we've done it, actually. We'll give you an idea of all the combinations that we see.
All right, so here's a little video for you showing the 3 different main ways that we've used to land onto Mars.
So you can see there, we're starting with the parachute. So we hit the atmosphere, we've got the parachute, and we've got 3 ways that we've been doing it. And we'll go through each one of those. We've got our retro rockets, we're just throwing stuff down. We've got these cool little sky cranes. So let's go through those. So surprisingly, maybe for some people, Viking 1 and 2, both in 1976, they used the parachutes to slow them down, and they actually used the retro rockets to slow and stabilize for landing. So you saw the ones with the airbags, those weren't our first ones. Our first ones actually used the retro rockets. So there's a really cool, this is some NASA promotional material from that time that shows everything. I love these retro diagrams, they're my favorite. And it shows all the steps there coming down, right? You've got it in orbit and its little orbiter drops it down. It slows with the atmosphere. You've got your parachute and you've got your retro rockets and it lands all nice with its little lander there, right?
Right.
Success, that's awesome. The next lander actually wasn't set until 1996. So that's 20 years later that they were like, hey, maybe we should visit Mars again. I think they tried in between there. So it followed a very different landing sequence here. So you can see already from the pictures that it's going to be a little different. You might remember from the video, but even a picture and the little animation can't really give you an idea of what it looks like. So we've got a really cool computer animation that we found that shows you just what this looks like. So you've got it hanging down from the parachute and it's got its airbags. And you actually do have retro rockets here too, just not as intense. And then it just drops it and it bounces. And it bounces, the first bounce throws it over 50 feet in the air. And it hits the ground so hard that it was subjected to 18 Gs. So the force of gravity we feel here, 18 times that. Just for comparison, a human can only take about 9 Gs and only for like a few seconds. So 18 Gs is what it hit there.
Crashing with style.
Around. Yes. They say flying is falling with style, so I guess it flew. Yeah. That was really stylish, in my opinion.
Honestly, this is definitely one of my favorite ways, because I just can imagine a room full of engineers thinking, how in the world are we going to protect all this really expensive, awesome science, payload? Well, let's just wrap it in a bunch of pillows. And they're like, well, we need more. There's just more pillows, like big, massive air bags. And then we're just going to like get close enough and then just cut it loose and just hope it like bounces to a stop. And that's what it did. And it worked. It was awesome.
Everyone was just like, yeah, man, let's do it.
Yeah.
It was really great because it did work. It was safe for the instruments and it was a lesser cost too. So because these spacecraft were small, they were able to, withstand that sort of thing there. So it made it a lot cheaper to send things. So we've got Spirit, Opportunity, Pathfinder, I believe, were the 3 that did that. Yeah. So it's cheaper, but it's also really intense. So like I said, although it was safe for those rovers to have that, there's still a lot of sensitive scientific instruments in there. So when you get, larger or more complicated equipment, so like Phoenix in 2007, InSight in 2018, they use retro rockets. So the Viking model with those retro rockets, it's tried, tested, true. Curiosity also used retro rockets like Vikings in 2012. So there were a few modifications though with Curiosity. And you might remember from the little video, there were 3 options there. There was the airbag retro rocket, and then there was one where it just kind of like let it down. So Curiosity's size and design meant that one of those legged landers there wouldn't have really worked well with the designs. So wheeling a rover off a legged lander really was a risk they didn't want to deal with. So instead they added another step in the landing. So the descent stage.
Go ahead and show you that stage here. Let's go ahead and bring it up for you.
Yes. So you have your descent stage, you've got your retro rockets, and then you see it's lowering it down. So instead of actually landing that descent stage with the retro rockets there, just turning them off and landing. It hovers above and lowers it nice and gentle and soft to the ground with those tethers, and it's called the sky crane. So they were long enough that these retro rockets also wouldn't like kick up dust too much that would cause issues with the machinery. And it's just placed nice and gentle on the ground while the descent stage, you saw it cut the cables and then just flew off to crash somewhere else.
Yep.
Yeah. So it was a brand new idea.
See you later.
Yeah, bye. And it worked perfectly. It worked. It was great. So these are our, 3 methods. And love to compare them, actually, so you can just kind of see.
Yeah, let me bring up a nice comparison of these all here. Oops. Here we go.
Yeah. So you can see there, you've got your retro rocket lander that comes all the way down. You've got your airbag pillow, and you've got your sky crane to just lower it down. So you can probably guess for Perseverance that it'll have a very similar landing sequence to Curiosity, because we've talked before about how similar it is to Curiosity. There are a few differences though. Its parachute's going to be a lot larger. This parachute is going to have a 70-foot diameter. So the one on the, what is that? The right, the left? I don't know my right and left, and I have just admitted that to everyone who watches this video.
The one on the left is the Curiosity parachute. The one on the right is the parachute for Perseverance coming up.
Yeah, the more checkerboard one is Perseverance, and it's 70 feet across.
There you go.
So the one before was 50 feet.
Yeah, you can see, it's kind of hard to see, but you can see there's some people. Well, on the left, there's a little cutout diagram of a person for scale. And then on the right picture, there is an actual person in there.
Pretty big. Yeah.
Big parachutes.
Yeah, we've got a couple of questions. We've got, what's the best landing site on Mars, from Denise? That is a great question, because there are, 2 big things that you have to consider. First thing is, why are you going to Mars? What are you looking for? So if you want to look for evidence of water, you wouldn't go to a place that scientists have said, oh, that looks like it was pretty dry. You go to a place that scientists say, I think there was water there. So if you look for water, you have to go to a place like that. The other thing that you have to consider is, how easy will it be to land? And this actually transitions really well into what we're going to talk about next here. And I wouldn't even call that a parachute. Yeah, same. So you need a good landing site. You need something flat. You need something nice. You don't want to create unnecessary challenges of like landing on a cliff. It's just, that's not fun. So a big addition to Perseverance's landing sequence is called this terrain relative navigation. So if you remember that communication delay, it means that a landing spot has to be very, very well planned out. You need to make sure that if you make a few mistakes at all, that you have a pretty nice, decent flat area that you'll be able to land or tumble around, I suppose, as it were, with some of them. So with Perseverance, the spacecraft will actually be able to assess a landing site itself and change its course to find a good, smooth, easy landing spot without the help of human input, which is really neat. Oh, yeah, you can see here. So it kind of like takes pictures as it's coming down, and the pictures will say, hi, this landing spot is not good. Maybe you should go somewhere else. And it'll move around and drop it somewhere nice. You can see in the animation, there's a nice flat spot. Let's use that. So that way it can do that without the help of human input. And if this landing sequence sounds as neat to you as it does to us, definitely join NASA for their live stream of the landing. It's going to be on February 18th. I don't know if you've ever watched a live landing before. Like the InSight one in 2018. I was there for that one. It was very exciting, very nerve-wracking though. So NASA calls descent and landing the 7 minutes of terror because anxieties run high through the entirety of the 7-minute landing over which they have no control. So join them, join us in that terror for 7 minutes. Yeah. But it's an incredible payoff though. Should be really fun. So we'll put a link in the description to the site where NASA posts all its live streams, so you can bookmark it and set a reminder.
Yeah.
Yeah. So we're really looking forward to it, and I hope you all are too. I'm excited to see how this new technology works, and that it does work. We can have some more successes, really bring our grade up with getting to Mars, especially now that we've learned a bit about what goes into landing a spacecraft on Mars and how difficult it is. You know, it's impressive feat. So, you know, cross your fingers and tune in February. I want to be sure I have time for any other questions though. So if you have anything that you're curious about, pop it in the chat there, whether it's about landing or Perseverance, Mars, or just space in general. Let us know in the chat because we're here to answer your questions live. If you're not watching live, feel free to leave a comment and we'll answer it in the next video or tune into the next video. So Denise says, do mathematics and physics change before, during, and after landing? So math and physics works pretty much everywhere. So it works the same on Mars as it would do on Earth or anywhere else. There's just different conditions. So although the math is the same on Earth and Mars, Mars has less gravity, it has different conditions. So you have different numbers that you're putting into the equation, which is really nice. If physics and math changed from planet to planet, I think our success rate for Mars would be like 1%, and that would have been the airbag one, maybe.
Yeah.
But yeah, good question. It's just different numbers. Let's see.
What other questions we have? Drop them in.
While we're waiting for any questions, one thing that I find interesting, if you've been thinking about this, is landing people on Mars. So when you get to landing people on Mars, one big challenge you could imagine is this landing sequence, because you can design instruments to withstand things, but you can't really make humans. Very right on top of it, could a human survive landing on Mars with the airbag thing? Probably not, unless we slow it down a lot more. Because before that airbag thing, like I said, 18 Gs, which is twice the amount of like force that a human can withstand even for a few seconds. If we could slow it down, I agree with Tara, if we could slow it down enough, that could be like a roller coaster ride of some sort.
Yeah, that'd be pretty fun, huh?
We could hit like just a couple Gs.
Now approaching Mars, everybody hold on.
So maybe, yeah, maybe don't toss it out just yet, but it would take a lot of tweaking.
Yeah.
An amusement park ride, yeah.
Great question.
I think I'd ride it. Do they test any landings, or do they test the landings, or do they just do simulations before they go? So we do a lot more simulations than we do tests, because simulations are cheaper than actually testing out all the equipment. But we do actually test them just to make sure that it does make sense and that it is going to physically work, because you can make things work in a computer that aren't actually going to work in real life. So if you are only plugging things into a computer, you might miss something that would happen in real life. So we do a bunch of simulations, but we also make sure that we're testing them here on Earth.
That kind of loops into this. This is a video of, I know we've talked about how Perseverance is going to have a little buddy there.
Helicopter.
The helicopter Ingenuity. So this is kind of just showing a video of how once Perseverance actually lands, that helicopter is going to actually kind of unfold itself, and then Perseverance will kind of drive away, and then it's going to go do its little flying thing on Mars to see how that works. But all testing like this happens a lot to make sure that things are going to be working before we send something worth billions of dollars to Mars.
Yeah, that would be really unfortunate. It looks like Tara dropped a link in the chat for some videos of their tests. I really love the videos of the tests. They're so neat. So why send humans to Mars at such a huge expense? I love planetary exploration, but robots seem the best way to go while spending research money here on our own planet. So that is why we do send robots a lot more to Mars. It's a really big question of when is it worth it to send humans versus robots, and where should we put our focus and money and things like that. And there's no one answer from everyone. There's no like consensus on it. So it's really up to personal opinion interpretation. Robots are definitely the way to go right now. There's a lot of challenges, and actually next week we're going to be talking about challenges with humans on Mars. One thing about the question of why are we researching this when we should be researching this is that there are a lot of scientists out there, and there's a lot happening. So just because we're looking at Mars doesn't mean we're not looking at Earth. our biggest project, NASA's biggest project really, is doing things with the Earth. Earth is the most studied planet. We have a ton of stuff happening with Earth. Space might be snazzy and everything, but we do a lot of stuff with Earth. So Mars is a really cool thing that we look at. It's new, it's fancy and exciting, but we are still doing things here on Earth. And we're waiting to send humans until we have a lot of data and we know that it's safe and worth it and things like that. But that's why we're sending robots more than we are sending people.
Yeah, great question.
Yeah, it's a great question. Definitely open for a lot of debate, interpretation. Does the Sky Crane come back to Earth, or do they just get launched into space? So I love this, the descent model, the descent stage that you see coming down with the retro rockets that drops it. So the actual crane itself just gets dropped, and then that descent stage just kind of flies off and crashes into Mars. I think they've managed to like take some pictures of where they've crashed on the surface.
Mm-hmm. Yeah, they're still there. You can there's like, I mean, there's all the other ones that have been used in the past. They kind of just go away, and then they just kind of crash in there. So there's, if you look around online, you can find images of these crashed these little crash descent stages that are just kind of sitting around. Maybe, I mean, that's one thing that maybe we could do some cleaning up once we get humans there. I'm sure that there's going to be a little bit of a trash cleanup right when we land. It's like, all right, let's go get all of these things.
Let's gather all the things that we have. Sorry about that. Yeah. Tara made a good point with that, that there's a lot of things that humans can do that robots can't.
Yeah.
For example, clean up.
Yep.
Gather those things. Yeah, we've got a lot of really good questions today.
Let's see. Any other questions about landing on Mars? I'm most excited to watch this actually happen live. I'm really, really excited come February. And yeah, we did post that link down below in the video description, so it'll always be there in case anybody loses it. Because I know I lose links all the time, but you can come back to this video and click on it.
We've got Charlotte would like to know, how do scientists know where water is on Mars? That's a great question. We actually do have a video about water on Mars, so you can get a really big explanation on this. But to make it a little smaller, can we kind of look at some of Mars here?
Yeah, I'm zooming us out here a little bit, and maybe I can bring up an elevation map too. That might be useful.
So if you ever look at satellite photos of the Earth, you can really tell where oceans are, you can tell where rivers are, where lakes are, because you see blue, right? You see there's water there, oh, there's water happening through here. We also see things like canyons, where even if we don't see the water, we know, water carved that. Where you see evidence of, oh, well, a lake used to be there. That's all we're seeing on Mars. We don't see the blue water, but what we see is the evidence left behind from water. Mm-hmm. So have you ever seen a picture of like a river delta? Where the river comes and it's just kind of flows out like that. We've got things like that. That's where Perseverance is going to land, in a river delta for a lake there. So we see evidence of, rivers, lakes, oceans. We see, canyons have been carved, outflow channels, things like that. So we see a lot of evidence for water interacting with the surface of Mars. So you can see evidence that there was water there.
Sorry, I'm trying to zoom us on over to Jezero Crater here.
Ooh.
We're slipping into nighttime here, but hopefully we can see some of these river channels coming out of the crater, because it's really, really cool.
It's really neat. Yeah, I would highly recommend checking out the Water on Mars video. We've got a lot of stuff with a lot of really specific information about like the evidence that we see there.
Ooh, getting in there a little bit close. Let me see, that might not be the best to see right now. Let me try to make it a little bit clearer.
It's a little dark.
Enhance.
Zoom and enhance.
Yeah. Let me see here. Let me put on a elevation map actually for us.
Yeah. Elevation maps, they'll just show you how high the ground is, and that can really show you a lot. It's how they do a lot of their research on how things look, because, you know, pictures in visible light, what you would see, they're really great, but there's some things that you just can't really pick up as well as when you look at it a different way, like the elevation map with radar. And as you can see, there's a lot of versions of elevation maps, layers, colors, things that you can do.
Yeah.
And each one is helpful in their own way.
It's loading up here for us, but it might be, it might take a little bit too long. It's a matter of how fast my internet can go. Try to rewind us in time a little bit to maybe get a little brighter for us. That's a little bit better. Let me try see if I can zoom in here real quick.
So you can see here, actually getting a little bit of a behind the scenes tour of how this stuff looks when we play around with it and when we're showing you things. There's a lot of menu buttons, a lot of things that you can see happening. And we all have to, or Jeremy, I don't have to do this. Jeremy has to keep track of what they all do and how they all work.
Jezero crater, where are you? Right in here.
While we're looking around, if anybody has any other questions, you can go ahead and pop them in.
See if hopefully I can get that map to show up.
So I've got it. I've got the picture showing here. I've got it here. So if I'm looking in a bunch of different places,
all right, well, we'll see if that one pops up. If not, is there any other questions that people have?
Tara dropped a cool link in the chat. There's a bunch of images from the Mars Reconnaissance Orbiter that's at Mars. So if you click that link down there, there's a lot of really cool pictures of things that the Mars Reconnaissance Orbiter does. It takes a lot of really, really neat pictures of the surface of Mars that shows all those. So how hot is Mars? So Mars is actually really cold. So Mars is a lot further from the sun than the Earth is, which means it gets a lot less sunlight. It also has less of an atmosphere that holds in all the heat, which means that it doesn't really stay warm even when the sun is trying to warm it up. The average temperature on Mars is about -80 Fahrenheit, something like that. That's colder than the South Pole. So it can get a lot colder than that. And I think like the warmest temperature I've ever seen is maybe in the 50s or 60s Fahrenheit. That's really not typical at all. Like I said, the average is like -80, something like that. So it's really, really cold. Sometimes we look at Mars and we see, oh, hot, desert, dry, must be hot. But just because a place is dry doesn't mean it's hot. Antarctica is actually the biggest desert on Earth. And then red is just what Mars is made of. It's rusty. But it's a pretty common question.
Yeah, not having much luck here with these maps, unfortunately. Sometimes it's going to take a little bit to load. It's trying to load there.
It's thinking real hard.
But I promise there's rivers, deltas on there. Maybe if we zoom out a little bit, there we go.
Oh, enhance. Yeah.
There's the crater. There's an elevation map for you, so you can kind of see. Maybe this we can highlight a little bit better. So blue colors are low lying. Green is a little bit higher than the blue. We'll see if it can load here. This crater right here. Oh, I guess you can't see my my mouse, but this crater kind of in the lower center here, if I move it right here, that's Jezero crater. And then you can see on the top end of the screen, there's like a little bit of like a little curvy line. So there's actually like a river that was flowing out of this crater, which used to be full of water back in the day,
a few billion years ago.
Yeah, a few billion years ago, and then you can see it on the
other day.
So, here we go. Now it's loading up here a little bit more.
Yeah.
See if this loads up, but you can see kind of like these river delta structures. This is on I think think this is on the west end of the crater.
Yeah.
There we
So
go.
you
You
can
can
see
see
that
how
delta.
this is where the water was flowing into the crater. Where Perseverance is going to land is going to be right on kind of the top edge of where the screen is now. And then it's going to kind of do like a little loop over nearby this little region and kind of explore this region more.
Yeah. River deltas are fantastic places if you're looking for life, because rivers bring a lot of sediment down to the bottom of river deltas. There's a lot of life that lives in river deltas, and then you also have both river and lake around there. So that's what really makes this a great landing spot. And you can also see there's a pretty good flat area around too.
Yep.
Lake beds are great for that.
All right. Well, I want to be cognizant of time. Looks like it's about 1:36 now. Are there any final questions that people have before we log off for the week?
Final Jeopardy.
What is the diameter of that crater? That is a good question. I'm thinking, I'm not sure if you're talking about the crater
about 49 kilometers.
Right, so probably not the crater that
30 miles.
We're looking at right here. This is a smaller crater. 𝐀𝐜𝐭𝐢𝐯𝐢𝐭𝐢𝐞 is, if we zoom out a little bit further, it's like the whole, you can kind of see this circular region here in the center. Rémy, did you say 49? Is that the size of 𝐀𝐜𝐭𝐢𝐯𝐢𝐭𝐢𝐞 crater?
Yeah, it's about 30 miles in diameter, 𝐀𝐜𝐭𝐢𝐯𝐢𝐭𝐢𝐞 crater.
30 miles in diameter. Okay, there you go.
It's pretty big.
There you go. Yeah, that other one, I used to think that little small one was 𝐀𝐜𝐭𝐢𝐯𝐢𝐭𝐢𝐞 crater. And so every time I was looking for it, I was trying to like zoom way in. And then I looked at a map like from way, further up in space. I'm like, oh yeah, okay, that makes more sense. The larger crater is 𝐀𝐜𝐭𝐢𝐯𝐢𝐿. And then,
all right, let's.
Yeah.
We've got a few other things next up, flying rovers. Well, that's what Ingenuity is going to do, actually. It's going to fly. We talk a little bit about that in, I think our last video talked a bit about Ingenuity and the challenges of flying on Mars, again, with less air. One of the ways that we fly is by using air. So it makes it really tough to fly on Mars, which is why Ingenuity is going to be pretty exciting. I hope we can get more flying things there. Plants on other planets, not yet. It's really tough to see things on other planets. They're so far away. Most of the time when we find planets, we're not actually even looking at planets. We're looking at how the planets affect a star. But we're always looking. Then snow falling on Mars. It does. Tara said yes. Awesome. It does snow a little bit, mostly at the poles though. Both water, snow like we have, but mostly carbon dioxide snow. It's just that cold. So dry ice. Spooky Halloween snow, dry ice. All right, if you all have any other questions, feel free to leave a comment or find our submission form, or come back for our show next week. Tara's going to be looking into the future to talk about putting humans on Mars. It's going to be our last video in the Perseverance to Mars series, so definitely come join us for it live. We're going to have a lot of fun. Same time, same place, Wednesday, here on the YouTube. I had a great time with you today, definitely over the past few months, and I hope that you all had a good time as well. And as always, if you enjoyed the video, don't forget to like it and pass it along to anyone you think might also enjoy it. And if you want more content, be sure to check out our podcast, A View from Earth, and keep supporting us here with your views. And make sure you subscribe to the channel if you haven't already. Turn on notifications, then you can get alerts when we post videos like these.
That's right. Yep, so I think that's about all. Until next week, guys, take care. Yeah, bye. Thanks for joining us.
Thank you. Have a good week.